All right. So in the last recording, I showed you a simple capacitor circuit, and showed you some possibly surprising behavior of a light bulb that was electrically connected, was wired together with that capacitor and the battery. And so now it's time to start going through the mathematics of what happened there. The secret behind all of this is going to be one of the things I said in the lecture on properties of conductors, and that is that the electric potential is constant everywhere on a conductor, everywhere in and on a conductor. So let's suppose I have a couple of conducting objects, and this time, again, I'm going to draw a couple of metal plates, typically squares. It doesn't look terribly square, but that's all right. Once again, I need to emphasize that the two metal plates are not in physical or electrical contact with each other, not at first, okay? And so what I'm attempting to indicate here is the existence of these two plates. They're separated from each other by a small distance. I made this drawing before. The distance between them is, we'll label it little d. And a thing that I want to point out, first of all, is that, and this is typical for capacitors, that the size, the dimensions of these metal plates, these conductors, the dimensions of these metal plates is much, much larger than the distance that we put between the two plates, okay? So whatever is between the two plates, sometimes it's air, usually it's some sort of plastic or wax kind of insulator for reasons that I'll explain in another lecture. Don't worry about why the insulator is there for now, I'll let you know it is. But anyway, it's important that the distance between the two plates be small compared to the dimensions of the plate. And here's why. Well, before I say that, and then we attach a wire to the top one, and we attach a wire to the bottom one. Stick that up there, okay? And those wires are just soldered on. They are actually part of the conductor, okay? And then what we do is we go and get ourselves a battery, and I'm going to put the battery over here just for a change. And in the demonstration I did in the previous recording, that battery was actually two D-cell batteries placed, stacked one after the other, and so their voltages, their potentials just added together for a total of 3 volts potential difference applied by that battery. And this little construct there, that is the symbol that we use to represent a battery, or more generally, any potential difference. And then I took a clip lead. In my demonstration, I used, I think it was yellow and green within a white one for the light bulb, but in my drawing here, I'll do blue and red. And so we connect the an alligator clip or some other kind of connecting wire to one of the wires coming out of the capacitor, and then we connect the other lead, the other wire, the other alligator clip lead, to the other wire to the capacitor, and attach both of these clip leads to the opposite ends of the battery. When that happened, we saw the light bulb light up. Now the light bulb itself was inserted into the middle of the circuit, and I'm going to represent the light bulb like this, okay? And the light bulb, as I say, lit. And the only way, and I'm just going to tell you this, the only way the light bulb could have lit is if charge was flowing through the bulb itself, all right? And it was, and so the goal here is to understand why that happened, why the charge flowed, and go through the mathematics. Well, I'll quickly go over the why the charge flow, because mostly I talked about it a couple of recordings ago. If we assume, as was true in my demonstration in the last recording, if we assume that the two plates were initially electrically neutral before we connected the battery, okay, then when we connected the battery, the top plate was connected to a location that had a potential of 3 volts up here. The bottom of the battery was at a potential of 0 volts, and 0 down there because we define it to be. And so there's a potential difference supplied by the battery. Supply potential difference, and the electric charges will automatically flow or fall from a high potential down to a low potential. You might recall that anything that would allow potential energy to decrease, any physical event that will cause potential energy to decrease, that physical event will happen spontaneously. This pin spontaneously falls from a location where it has a high gravitational potential energy to a location in space where it has a low gravitational potential energy. Exactly the same thing is true of the charges. There's positive charges on this there's positive charges on this top plate. When we attach it to the battery, they suddenly get placed at a potential of 3 volts. So they're at a high potential, but they have a path from the top of the plate through the battery to the bottom of the plate, so they can fall from a high potential down to a low potential, and so they will spontaneously do that. And so the charges will flow from the top plate down to the bottom plate, but of course, since we inserted the battery in the path, the charges have no choice but to pass through the battery on their way to the bottom plate. And when the charges flow through the bulb lights. However, as I explained earlier, as the transfer of charge continues, a larger and larger potential difference starts to build up across the plates that is the opposite of this potential difference that's driving the whole process. And so eventually, enough charge gets transferred that a new potential difference has been created in addition to the potential difference of the battery. And when the potential difference between the plates over here becomes equal and has the opposite sign of this potential difference, the total potential difference from here to here becomes 0. No net potential difference anymore. No reason for the charges to flow or fall to a low potential anymore, because there is no low potential anymore, and the charge stops. But, and so much I've said before, but now let's look at the intermediate stages. At some point, and I'm just going to make up a number here, at some point in the charging process, let's say the potential difference between the plates becomes -1 volt. Okay? So that means it's a positive 3 volts caused by the battery, a -1 volt caused by the amount of charge that has been transferred so far, let's say within the first 1 second or something. Okay? And so the net potential difference is now just 2 volts. Since the net potential difference is somewhat smaller, the electric field associated with that potential difference is also smaller. Since the electric field is smaller, the electric force driving the charges is smaller. Since the force driving the charges is smaller, the rate at which the charges flow is smaller. But that means that the charges are not moving as fast through this light bulb. A smaller movement of charge, a smaller current, as it's called, the dimmer the bulb becomes. Okay? And that's why the bulb got dimmer and dimmer and dimmer as time went on, because as time went on, the potential difference became the total potential difference, battery plus plate separation. The total potential difference became smaller and smaller and smaller as time went on, which means the current became smaller and smaller and smaller, which means the battery's brightness became smaller and smaller and smaller. And eventually, the current became so small that it wasn't even enough energy to light the bulb anymore. The light goes out, and that's what you saw. Okay? All right. So that's the physical explanation for what happened. Now let's cast this in mathematical form. Having, for the most part, for the most of the rest of this explanation, I'm going to pretty much ignore the existence of the light bulb. Again, the only real reason that the light bulb was there was to allow you to see that something was happening. All right, so having placed the battery as I did here, and now I want to do this with general symbols here. So let me refer to these as the potential at the positive end of the battery, and down here I'll call this V sub negative for the potential at the negative end of the battery. Okay, and the potential difference between them is V positive minus V negative. So this V here is just the potential difference between the top plate and the bottom plate. Okay, and of course that's how you calculate it, the one potential minus the other potential. But that potential difference is equal to the negative of E times D. Okay, first, okay, let's back up. What electric field? Well, the electric field that the battery creates across the capacitor. Okay? And D, of course, is the distance between them. And this makes sense because we have an electric field. We have charges moving overall. The charges are originally on the top plate, they end up on the bottom plate, so the total net distance that the charges moved is this distance D. Okay? They moved up but they fell back down again, they moved down, but then they moved back up again. Their net displacement was just D. Okay? So E times how far they moved, I've talked about this before. Remember that V is equal to E over D. Actually, the way I wrote it before was am I doing that right? I'm sorry, wrong. I'm sorry. E is equal to minus V over D. What I actually wrote in the past was something like E is equal to minus delta V over delta D, but those aren't the symbols that I happen to use in this case. Instead of delta V, I just called it V. Instead of delta D, I just called it D, but it's the same ideas. Okay? All right, so the point being that this is the mathematical relationship, or this one is, that relates the electric field created by the battery to the electric potential created by the battery to the distance between the plates. All right. Then the question becomes, okay, what's going to happen? And the answer is transferring charge from the top plate to the bottom plate. Eventually, the process stops, which means that there's apparently a maximum amount of charge that I can transfer, because at some point the charging process, the transfer process stops. So hooking all this stuff up, I don't charge the capacitor forever. There's some limit, and the question is, what is that limit? What determines it? How do we calculate it? This lecture's gone on long enough. Let's skip to the next one.